So hello everyone. My name is Salewa, and I'm a senior at SUNY Poly, and I'm here to present to you the research that I've been doing for the past year at the Masonic Medical Research Institute. So let's start off with an introduction. So basically, the purpose of our research is to come up with a fluorescent probe that can image the bone healing process, so we can monitor it, study it, and hopefully come up with a better treatment for the patients. And so bone fractures are really common, right? There are more than 16 million fractures happening in the United States each year. And if we take a look at something like osteoporosis, they often lead to fractures as well. And sometimes fractures can further be complicated by things such as infections and bleedings. And these problems can be troublesome. And so it's really important to come up with something that could potentially help in treating bone fractures, right? So now you take a look at the anatomy of the bone. I'll zoom in onto this image right here. We can see that bone in the nanoscales is mainly composed of these HA crystals, right, or hydroxy apatite crystals, right, and these hydroxy apatite crystals are calcium minerals, right? They're really important for healthy bones and teeth and stuff like that. And so if we have a fracture and the bone is rebuilding itself, we would expect a lot of these hydroxyapatite crystals deposition, right, in the fracture site. Going back to osteoporosis here, the reason there is a loss of bone density is because of the loss of hydroxyapatite crystals, right? And there are ways to prevent the loss of these hydroxyapatite crystals. There's this drug called biphosphonate or BPP. I'll show you the structure here. It's basically a compound composed of two phosphate groups, right? So the really cool thing about BPP or biphosphonate is that it binds really well to hydroxyapatite crystals, right? So it prevents the loss of bone density. So if we take advantage of the interaction between hydroxyapatite crystals and BPP, let's say if we connect a BPP to a fluorescent dye, this BPP connected to the fluorescent dye will then bind to the hydroxyapatite crystals, right? So in this case, we should be able to image the deposition of hydroxyapatite crystals, right? Especially in bone fractures. So now this is where the dye synthesis comes in. It's a major part of our research, and let's move on to this section right here. So a typical dye consists of an end group and a linker, right? So to make the end group, you just take this indole compound right here, you add some sulfuric acid to it, you add TBAB, you heat it up for an hour or so, you get the end group. And then to make the linker, you just take this compound right here, you add a bunch of compounds in, you heat it up, you get the linker. And this is the structure of the dye itself. In the middle, we can see that we have the linker in the middle right here, and at the end we have the end group from each sides. Now in order to connect a BPP to our fluorescent dye, we first need to activate the dye itself, right? So we can activate the dye by adding NHS to it, and when the dye is activated, we can couple the dye with biphosphonate, two phosphate groups right here, by adding things such as DMF, triethylamine, along with the coupling reagent, right? So we actually try to use many different type of coupling reagents to see which one would give us the most yield of the product. And if you would take a look at this table over here, we kept all the conditions the same, all the reactant concentrations the same for all three entries that we did. Excuse me. So in the first entry, if we use EDCI alone, we get less than 15%, right? And on the second entry, if we use PyBob alone, we get less than 15% too. But if we on the third entry, if we use EDCI and DMAP together as the coupling reagent, we get somewhere between 25 to 30% yield, which is the most yield. So now that we have our probe to see whether we can image the fracture site or not, we actually send our probes to our collaborators where they do the imaging themselves, and this is the data they gave back to us, right? So we're comparing a fractured bone to a non-fractured bone right here, and this top one is a fractured bone and the bottom one is a non-fractured bone, right? So clearly we can see here there's a very dense concentrated spot over there, and that's where the hydroxyapatite crystals is concentrated, right? It's where it's deposited and it's the site of the fracture, right? So So clearly, this experiment is a success, right? We have our probe, we have the data over here that's supporting our experiment or our hypothesis, so it really works. And obviously there are more to that, to bone repairing, than just hydroxyapatite crystals deposition, right? There are things such as fibrin formation, collagen fiber collagen fiber formation. And to see the formation of collagen and fibrin, we can use the same concept of having a coupling agent, right? And then couple it with our fluorescent dye, and then see the image, just like how we did, just like how we coupled BPP to our fluorescent dye, right? So in that case, to see fibrin, we just need a fibrin targeting peptide, right? And then couple it with our dye, and then we can see fibrin. And to see collagen, we use a collagen targeting peptide and couple it with a fluorescent dye, and then we can image the collagen formation, right? And if we take a look at this table over here, we have a fibrin formation in the early stages of bone repairing, right? And we have a collagen formation in the later stages after day 21 or so. So yeah, this is our research project. In short, we just made some fluorescent probe that can image and monitor the bone healing process. And hopefully our probe will be useful for patients as well as doctors in clinical settings. And I just want to thank you for your attention. And if you have any questions, just write them below and I'll try my best to answer them. Thanks.